All right. Hey guys. So we are moving on to 6.2, day 1. This section, like the previous one, I'm going to break up into 3 different days. We'll have 3 lessons, a worksheet day, and a quiz day, so 5 days total here. The main focus is definitely going to be on finding volume. We'll talk about density a little bit and average value a little bit, but focusing on volume. So keep in mind the whole idea that an integral is the summation or adding up of the values, and integrating or anti-deriving always adds an exponent or adds a degree. So therefore, in this section, in order to get a volume, we're going to integrate an area. If we add up all of the areas, we end up with a volume. Okay. So for me, for this type of stuff, for this type of section, again, if we're doing a volume, we're doing a solid. So I like to visualize a loaf of bread. Okay, a loaf of bread can be sliced, right, into different cross sections, is what we're going to refer to them as. A typical loaf of bread that we buy to make sandwiches with, the cross sections are squares. A loaf of bread that we might have at dinner or something like that would be more, if we sliced it, you might have a cross section of a semicircle. So the different problems in this chapter or in this section will have different shapes of cross sections. Our job is to figure out, well, what's the area of one of those slices? And if we add them all up, then we have the volume of our loaf of bread. All right, so the formula here, written in math of what I just said, is we integrate from point A to point B the area of the function. So like the previous section, we can go in both directions. We can have the area with respect to y values, or we can have the area with respect to x values. So today we're going to focus on what you have here, area with respect to y values. So y's will be inside of our integral, therefore a and b, the limits of integration, need to be y values from the graph. So our steps, number 1, we're going to sketch the graph. Functions will be given. You're finding the space, the shaded region, just like we did in 6.1. But we're not integrating from there. The second step, based on what the problem describes, we're going to find the area of one of the cross sections. We're going to find the area of one of the slices. And then finally, once we have the area of one slice, we integrate, and that gives us our volume. So this is a nice example because the drawing is laid out for us. Don't get too intimidated by this. The drawings that we're going to come up with are much simpler than this. But to start us off, the problem is asking for the volume of the solid whose base is the region between the parabola and the x-axis. So I skipped some of the words in there because they're really just fillers. They make it sound a lot more complicated than it is. In our graphing calculators, in Desmos, we're just graphing 4 minus x squared. Right, and that's giving us this parabola and the x-axis. So we have our shape right there. Okay. Now, in 6.1, we would find the area of that shape. In 6.2, we're turning that area into a volume. And let me keep reading. So now it says we have vertical cross section, so something's coming up off the page is the way I think about it, or out of the graphing calculator. These cross sections are perpendicular to y. So that can be translated a couple of ways. I can say parallel to x. I can say horizontal. And ultimately, if I'm running horizontally along the graph, I need to be thinking in x equals terms, or in terms of y. So I'm going to use that in a second. But for now, if I'm horizontal, right, all of my slices are running this way. If I needed to cut a semicircle, because that's what the problem tells me, and that's what the picture obviously is, all the cross-section are semicircles. So if I wanted to slice this, right, and have one slice, sort of like my slice of bread, I would have to slice it horizontally, and then I'm going to draw it flat on the page. And the horizontal part is consistent with my three-dimensional picture. Okay. Now my focus isn't on the big three-dimensional picture, it's on this simple semicircle. And I'm thinking about, well, I need the area of this semicircle. So a semicircle is just half of a circle, so 1/2 pi r squared. So I need to figure out what is this radius. I don't want the radius as a number, I want the radius as a function, because the radius at any given moment here, right, is going to change. And it will change dependent upon where I am on the parabola, right? The x coordinate of all these ordered pairs would give me the distance, the radius. So I need to take my 4 minus x squared and solve it for an x equals equation so that I know what my x value is. So I would add x squared, subtract y, and I would square root. Right? Now, because of symmetry, and we're going to see this in the next examples as well, in this case, the symmetry of the parabola helps me, because with a semicircle, right, I don't want the entire distance. That's why when I drew this picture on the left over here, I put my point in the middle, and I only went in one direction, because the radius is half of the diameter. So the x equaling square root of 4 minus y is exactly my radius. The distance from the y-axis to the parabola on one side. So I put square root of 4 minus y into my area equation. You can simplify it or not, that's up to you. But ultimately that area formula just goes into my integral. So square root of 4 minus y squared goes to 4 minus y. When it's easy like that or obvious like that, I would simplify it. If it's a little bit more complicated, just leave it as is and put it in the calculator. All right, so now my last step, always keep this as your last thing. Look inside your integral. What variable or what letter is in there? We have y's. So now we go to the y-axis to find the smallest and the largest value that's bounding the shape. So the x-axis, or 0, and the vertex, or 4. Okay, so we go to Desmos. My answers are hopefully still in there. And they are. So the first one typed in, 0 to 4, 1/2 pi, quantity of 4 minus y dy, using parentheses correctly, gives you 12.57. And this is a unit cubed for volume. Okay, this is one of those lessons that you're going to want to maybe watch these examples a few times. Try to find the distinction between today's lesson, the next lesson, and the third lesson. This lesson is going to be very consistent. All of the slices will run the same direction, and then we'll move to the next type and the next type. So you'll have consistency within each day. And of course they do flow together, but they will be different types of problems, okay? All right, so find the volume of the solid with a base enclosed by x plus y equals 1. This should say within the first quadrant. With cross sections perpendicular to y, semicircles. So again, translate parallel to x. Horizontal, x equals. Okay. Get the basic graph, x plus y equals 1. I like to think of that as y equals negative x plus 1. So that has a y-intercept of 1, a slope of negative 1, so down 1 and right 1, which is going to give me a line. So if I'm bounded in the first quadrant, right, I just have this triangular shape, which really doesn't signify anything. The fact that it's a triangle doesn't really help me out. Okay. Our shape that we're focusing on are semicircles. They are horizontal. So when I draw my pictures, that word horizontal is really, that's the main focus of my drawing. That's the direction that everything's running in. You know, I'll draw one or two of the cross sections. So I have a semicircle, just to remind myself that these semicircles are different sizes. Now this time, I don't have that symmetry that I had before, right? I'm not crossing over the y-axis. So now my semicircle, one side of it is on the y-axis, and one side of it is on the line. So cut it, lay it flat, horizontal, horizontal, how I drew it. Okay. So my focus is, if I want the area of a semicircle, right, always try to simplify these down to geometry problems. My only job right now is to figure out what's that radius. What's the distance between the middle of my semicircle to that line? So middle, that keyword there, because radius is just half of a diameter, I need to do exactly that. I need my equation, the given equation, to be written as an x equals. So x equals negative y plus 1. And then I need to cut it in half. So my radius is negative y plus 1 divided by 2. Right? The x equaling negative y plus 1 gave me the entire distance from y-axis to line. For the radius, I only want half of it. So area equals 1/2 pi negative y plus 1 over 2 squared. Integrate that. Okay, be careful with your parentheses. And again, final step, limits of integration. I have y's inside of there, so my lowest value and my highest value on the y-axis, 0 until 1. So my second one here gives me an answer of 0.13. Units cubed. Okay. Just one more example for today. Find the volume of the solid with a base enclosed by y equals x squared and y equals 3. Always start by drawing. Use your graphing calculator. You don't have to do these by hand. But drawing that two-dimensional graph. Thinking about, okay, what is the base? What's the enclosed region? Maybe I need to find points of intersections. Maybe not. But key points on my graph. Okay. Then I keep reading. So cross sections perpendicular to y are squares this time. So perpendicular to y, parallel to x, horizontal, x equals. Okay. So my slices are here. And this time when I slice it, or whatever, if I think about it as what's coming out of it, I have squares. And those squares are dependent upon my parabola. Slice, lay flat on the page, corresponding dimensions as you see. Okay. So I have area of a square. So I need to figure out what the side is, and then I square it. So for a square, of course, unlike a circle, I need from one side all the way to the other, right? But my y-axis is bisecting it. That was a good thing with circles, because circles you only want half. You want the radius. It's not a good thing with a square because we need the whole distance. So we're going to actually have to double this. So we take y equals x squared, we first solve it for x equals square root of y. X equaling square root of y only brings us from y-axis over to parabola at any given moment. We need the other direction as well, so we need to double root y. Another way to think about this is the fact that if I solve with square roots, I apply a positive and a negative. So one example of y equals x squared, where a solution of that, x equaling root y, would be 1. But another solution of that would be negative 1. So if I think about that as a distance, right, negative 1 until positive 1, that distance is 2. I'm doubling it. Okay, so now I'm going to integrate 2 root y squared, which is 4y, from lowest to highest, 0 to the horizontal line of 3. In my calculator will give me 18. Units cubed. Okay, so this was just day 1. We have 2 more days of lessons, a day of a worksheet, a day of a quiz. So this will bring us all the way until the end of next week. Okay. Reach out if you have any questions. I'm happy to hold office hours for you. Small individual one-on-one sessions, or we can have small group, whatever you guys feel like you need. Reach out. Take care. Hope to see you soon.